Hello ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be looking at Lewis acids and Lewis bases. So we've already talked about the Arrhenius definition, we've already talked about the Bronsted-Lowry definition of acids and bases, so now we're getting into Lewis acids and Lewis bases. So Lewis acids and Lewis bases are named after this guy. Gilbert Lewis, the one who, I was going to say invented, I guess that probably isn't the best term, but devised Lewis dot structures. And so go figure, in order to figure this stuff out, you need to draw Lewis dot structures. But the first thing you need to know is that a Lewis acid is defined as a non-bonding electron pair acceptor. So that means that it is able to accept a lone pair of electrons that is not in a bond from something else. So those little lone pairs of electrons that we've been drawing on things, Lewis acids are going to be the ones that accept them. In other words, the one that is attracted to it. Lewis bases, on the other hand, are the ones that are donating the non-bonding pair of electrons. So that means they are the ones that have those lone pairs of electrons on them. They're the ones that are going to be doing the donation part. Okay? Now, here's a weird little fact, but notice that even though the Lewis acid and base stuff that we've been talking about right now, it actually applies to Arrhenius acids, and it also applies to Arrhenius bases. It applies to Bronsted-Lowry acids, and it applies to Bronsted-Lowry bases. It's just the other two definitions that we've been discussing are a lot easier to picture and a lot easier to describe, because when we're doing Lewis dots, that means we actually, need to draw the Lewis dot structures for things in order to figure out if they're Lewis acids or Lewis bases. So for example, here is the Arrhenius definition of an acid and Arrhenius definition of a base. Now look at OH minus. It has a lone pair of electrons that it can donate. That means OH minus is a Lewis base. And remember, that's what an Arrhenius base was anything that has OH minuses. Now, Lewis acids, okay, are the ones that are accepting it. Notice H plus doesn't have any electrons. It will easily accept this non-bonding pair of electrons here. And now we have a Lewis acid because this is going to accept the lone pair of electrons from the hydroxide ion. Now let's just pick another random example from our Bronsted-Lowry ones that we were doing, right? So there are no lone pairs that you can see on here, but you kind of already know where the lone pairs of electrons are located. So if these are our reactants and these are our products, this H is going from here to here. And that's how we defined Bronsted-Lowry acids in this case, and Bronsted-Lowry bases. But if we're looking at the electrons, what's actually happening with the electrons? So think about this. We have two lone pairs of electrons on this water. These are non-bonding pairs of electrons, and that means that the hydrogen is going to be accepting those electrons in order to make H3O+. So what does that mean? That means this is a Lewis acid, and this is a Lewis base. Notice, still works. It's just now instead of looking at hydrogens, we're looking at electrons. So we're looking at the opposite. So a lot of times people say, oh, look, Lewis acid is totally the opposite. It says acceptor, where that was actually, the base. Or it says, oh, look, Lewis bases, it's the donor, where that was the actual definition of the Bronsted-Lowry acid. But think about what is being donated and what's being accepted. In the Lewis acid and Lewis base cases, we're looking at negatively charged electrons. So in the case of the Bronsted-Lowry definition, we're looking at a positively charged hydrogen. So the reason why they're opposites here is because we're looking at oppositely charged things. So here are two examples. I have aqueous oxide ions that are reacting together with sulfur trioxide gas to form aqueous sulfate ions. Identify the Lewis acid and Lewis base in the reaction. So let's see if you can remember. So oxide ions and sulfur trioxide gas, what would those look like? Well, that would be oxide ions, and this would be our sulfur trioxide gas, SO3. Sulfate ions, SO42-. Okay, great. So which one of these two would be our Lewis acid and our Lewis base? In order to actually figure it out with 100% certainty, we would need to draw the Lewis dot structures. So here's what the Lewis dot structures look like. This is oxide, this is sulfur trioxide gas, And then this is a poorly drawn sulfate ion. Remember, we talked about how it can have an expanded octet. So if we were drawing this exactly the way it exists, you would actually have a double bond here and a double bond here. And we would, use our two pairs of electrons to make them double bonds. But in reality, it doesn't really matter. This is just one way of drawing a sulfate ion. It's just not an accurate way of drawing a sulfate ion. But let's take a look, right? So this oxide is going to donate a lone pair of electrons to this sulfur here, and then that is going to create a bond forming our sulfate ion, right? So that means this is our Lewis base because it's the one that is donating the electrons, and then this is our Lewis acid because it's the one accepting those electrons. Now let's take a look at this one. This one, just again, look at the before and after picture here. We have our reactants, we have our product. And so it's asking you which one's the Lewis acid, which one's the Lewis base. So again, we have Lewis dot structures drawn for us. What do we notice? We should notice that this has a lone pair of electrons, this doesn't. So this is going to donate its electrons, and this is going to accept those electrons and form this complex here. So that means this would be our Lewis acid because it's accepting electrons. This means this would be our Lewis base because it is donating those electrons. All right, so that was a little bit about Lewis acids and bases. If you have any questions, let me know in class.